Let us discuss about types of semiconductors. Generally, the semiconductors are divided into two types, intrinsic and extrinsic. So, one is intrinsic, second one is the extrinsic semiconductors. These intrinsic semiconductors are nothing but the pure semiconductors, and we are going to call extrinsic as impure. Okay, the pure form of semiconductors are called as intrinsic semiconductors, and the impure form of semiconductors are called as extrinsic semiconductors. That means when you add an impurity to intrinsic semiconductor, it is going to become an extrinsic semiconductor. So, what is an intrinsic semiconductor? A semiconductor which is in its extremely pure form. Which is in its extremely pure form is known as intrinsic or pure semiconductor. That means it has to contain only either silicon atoms or germanium atoms in its covalent bond. If you consider silicon, that has to form a covalent bond with only silicon atoms. That means the entire crystalline structure of a semiconductor contains only silicon or only germanium. Then we are going to call them as intrinsic semiconductors, like this. See, here I have considered 4 silicon atoms. The outermost electrons are going to form a covalent bond with the adjacent valence electrons. Adjacent atoms valence electrons. So, all the atoms here are silicon only. For example, I have considered few atoms like this. So, if you observe here, there are 4 electrons in their outermost shell. I have considered the valence electrons. In all the atoms, I have considered valence electrons for explanation purpose. If you observe, each atom contains 4 electrons in the outermost orbit. So, these electrons will form covalent bonds with their neighboring atoms. So, this atom will also form covalent bonds with neighboring atoms. I have not shown that. But each electron will form a covalent bond with the neighboring atoms. If you observe, all the atoms are here are silicon, and these are called covalent bonds.
Intrinsic semiconductors. Intrinsic. And the word intrinsic in the context of semiconductors can be thought of as pure. So it means all atoms are identical, or all atoms are same. So if you're dealing with an intrinsic silicon semiconductor, all atoms must be silicon. If it's intrinsic germanium semiconductor, all atoms must be germanium. Think of that. All right. What we'll do is we'll explore the electrical properties of these semiconductors. And what we'll find is this. You see, for metals, there are only one thing that's responsible for electric current. Free electrons, right? But for semiconductors, turns out there are 2 things responsible for electric current. One are the electrons. What are the others? Well, we'll find out in this video. So we'll take a specific example and work with it. So let's say we take silicon. Okay, we'll first look at how a silicon forms a crystal, and then we'll look at its electrical properties. To do that, first let's write down the electronic configuration of silicon. Silicon has 14 electrons. So its electronic configuration would be 1s2, then it will have 2s and 2p. They will be completely filled. You have 2 and 6. That makes it 10. So 3s and 3p will also be involved. And 3s will be 2, 3p would be just 2. And you may have already studied in chemistry that atoms love this thing called as octet structure. They would like their final energy shell. They would like their final orbit to be final shell to be completely filled with electrons, 8 electrons, octet. Our silicon only has 4 electrons in its final shell, right? So it needs 4 more. How does it get that? Well, if you take a silicon crystal, where all atoms are silicon, all atoms are in need of these 4 electrons. So guess what they will do? They will end up sharing their electrons, and this is called as covalent bonds. So silicons end up forming covalent bonds with each other. And so if you could see that, it might look somewhat like this. So here it is. I'm going to draw. These are the silicon atoms which are covalently bonded with each other. All right. Now don't take this diagram too literally. All these lines are just for representation. But here's the way to think about it. Look at this silicon atom, for example. It has 4 outermost electrons. These are the 4 electrons. We're not showing the innermost electrons. And what the silicon is doing is it's sharing with 4 of its neighbors. And so as a result, notice each silicon atom has now 8 electrons in its vicinity. So you have 1, 2, 3, 4, 5, 6, 7, 8. So this silicon is happy. And look at this silicon. It's even this one has 1, 2, 3, 4, 5, 6, 7, 8. That one is not shown. So all silicon atoms have 8 electrons access to it, and as a result of this sharing, they're all happy. And in fact, this is what keeps the entire crystal together. Okay, so now the big question is, what about its conducting properties? Can this silicon conduct? Well, that really depends upon the temperature, it turns out. So what we'll do is we'll start off with very low temperatures. Let's go absolutely low. Let's go to absolute 0. If you're at the very low temperature, like very close to absolute 0, what do you think will the silicon crystal do? Will it conduct? Well, it has so many electrons, right? But the question is, can they conduct? The answer can only be given by looking at the band diagram of this. In previous videos, we've spent some time talking about this band structure, band theory of solids. And if you need more clarity or you need a refresher, it would be a great idea to go back, watch those videos, and then come back over here. But anyways, you would see that for semiconductors, the valence band, the band which has highest occupied electrons, the valence band, is completely filled. And then you have this gap in the energy, which is not allowed for any electrons. We call the forbidden energy gap. And then you have this next energy band, which electrons can occupy. All right. And at absolutely 0 Kelvin, all the electrons have occupied these states. So if you were to look at individual states, we'll just draw that, we'll show that. So if you were to look at the individual states, recall that a band is actually a collection of all these states. I'm now showing some of those. Then each state has 2 electrons in it. Remember Pauli's exclusion principle? One will be upspin, one will be downspin. A third electron can't be over here. The next electron will be on the next state, and so on. All these electrons are filled in this valence band, and there are no empty states available. As a result, if we were to put an electric field over here, none of these electrons could conduct. And the reason for that is, if an electron wants to conduct, if it wants to accelerate, its energy should increase, right? More kinetic energy. And so none of the electrons will, well, if the energy has to increase, well, there has to be an energy state available for the electron to go to, right? But all the energy states are filled, so the electron's energy cannot increase. And as a result, none of these electrons will conduct. And so this whole solid acts like an insulator. So at 0 Kelvin, this whole material acts like an insulator, and the reason it acts like an insulator is because, well, there are no empty energy states available. So what happens if we increase the temperature? Let's say we bring it all the way to room temperature. Well, let's find out. I have it ready down over here. Excellent. So imagine we are now at room temperature. Let's say that's about what? That's about 300 Kelvin. What will happen now? Well, now at this temperature, there's a lot of thermal energies available. And as a result, some of these electrons can absorb this thermal energy and jump or get excited from valence band into the conduction band. So maybe this electron over here, maybe that one absorbs some thermal energy, gets excited, and maybe it jumps all the way to this state. And maybe that electron, let's say, is this electron over here. And so as a result, now if we apply an electric field, this electron is free to move. Why? It's free to accelerate because it can increase its energy further now because states are available. It couldn't do that before, but now it can. And so we're going to say that this now is a free electron. And to show that, for representation, we're going to put that outside the covalent bond, saying that it is not stuck over here. It is free to move around, and it can do that. And notice, not only did we get a free electron, but because that electron, now imagine that electron moves away somewhere. And because of that, notice there is a vacant space available. In the valence band, this state is now free for some other electron to come and occupy. And because there's a lot of, thermal agitation, maybe this electron goes and occupies that. So maybe this electron goes and occupies that. And you may be asking, like, why would that electron do that? It's randomness. Before it couldn't move, but now there's an empty state. It can move. It's random. All right. So as a result, in the valence band, if you look at the band diagram, maybe that electron was, I don't know, maybe it was this electron or maybe this electron, I don't know. So that electron will now go and it has taken this space. And as a result, the vacant site has moved. Now that this is the vacant site. And maybe another electron, maybe this electron now can take up this site. All right. Maybe it's this electron. That's the one that's going over there. So, all right, all I'm showing is showing some electrons jumping from one place to another due to thermal randomness. And notice, as a result, can you see that this empty space, this vacant space, sort of feels like it's moving around? Does it make sense? So instead of saying it's the electrons that are jumping from one place to another, what we like to do is we like to think that this vacant space itself is moving freely. I know it doesn't make sense because vacant space is not a particle to do that, but we like to think of it that way. So what we like to do is we like to put a circle over here, and we're going to call that thing as a hole. All right? We're going to call that as a hole. And the whole idea behind this hole is that we think of hole as a particle, and we think of it as freely movable. So we're going to assume that it can freely move throughout this entire crystal. All right? And that's why we get current due to two particles. One are the electrons, and another one are the holes. And guess what? These holes act like positive charge carriers. And here's why. See, imagine if you were to put an electric field like this. If you were to put an electric field over here, then notice this electron, this free electron, will accelerate this way, right? It will accelerate in this direction. And similarly, this electron it's not free, but it can jump from here to here. And as a result, it seems as if the hole has moved here. And then the hole moves here, and the moves here. So can you see that this hole, it's as if the hole, if you treat it as a particle, it's as if the hole is moving in the same direction as the electric field. Does it make sense? And that's why we like to think of holes as positively charged particles. And so in semiconductors, there are two things responsible for current. One are the electrons, but the other ones are holes. A couple of notes to end the video. First one is that even though holes we treat them as positively charged particle, don't think that they are going to attract the electrons. They don't attract the electrons at all. You can think of them, they're independently moving. All right. But of course, if an electron comes very close to a hole, yes, it can fall into that hole, but don't think they're attracting each other. Another thing is with the band diagram. Notice that if you were to carefully draw the electrons in the band diagram, we have to be so careful that we cannot put more than 2 electrons in a horizontal line, because you see, each level can only have 2 electrons maximum, right? With one upspin and one downspin. But that makes it so tedious to draw all of this. And so you know what we'll do usually? Usually we forget about all these energy levels and we randomly draw electrons everywhere. I know that's not very accurate, but that's easier to draw. So if you were to show electrons and holes over here, from now onwards in future videos, I'll just draw them like this. I'll just show a few electrons over here all around. In reality, only 2 electrons can occupy a particular state, but let's relax that now. And then I'll show a bunch of holes over here. And we'll imagine these are all freely moving. Okay, so it's not very accurate, I repeat, but it's easier to draw that way. And this is very easy to represent that. All right, one last thing. Let's end with an analogy. I like to think of these electrons as water in this water bottle. This empty water bottle is just like a conduction band with a lot of space, and as a result, water can move freely through it. And you can think of this valence band, which is completely filled with water, as a completely filled water bottle like this. But the holes then will represent these tiny air bubbles. These air bubbles are like vacant sites. These are the places where the water should have been, but it's not there. And as a result, even now, notice these air bubbles seem to move. Of course, in reality, it's the water that's actually filling up that place and that vacant site ends up moving, but it really feels like this air bubble itself is a particle. So that's the idea behind holes. And that's why we like to think of holes as a particle.
Extrinsic. Extrinsic semiconductors are nothing but impure semiconductors. That means when you add impurity to the intrinsic semiconductor, it becomes extrinsic. Intrinsic plus impurity is nothing but extrinsic. The addition of an impurity to a semiconductor is called doping. So we are going to call the addition of impurity to a semiconductor as doping, and that impurity is going to be called as dopant. 2 types of impurities can be added to the intrinsic semiconductors: donor impurities and acceptor impurities respectively. And what are these donor impurities? Pentavalent impurities. And what are the acceptor impurities? Trivalent impurities. And what are actually intrinsic semiconductors? They are tetravalent impurities. So these semiconductors, which the silicon and germanium belongs to the 14th column of the periodic table. The silicon semiconducting materials belongs to the 14th column. So all these elements will act like semiconductors, and the most frequently used semiconductors are silicon and germanium. So all these elements that are present in the 14th column contains 4 valence electrons. Now the elements that are adjacent to it, that is the elements that are present in the 13th column, will contain 3 valence electrons. That's why we are going to call them as trivalent impurities. So the elements that are present in the 15th column of the periodic table will contain 5 valence electrons. That's why they are going to call as pentavalent impurities, and examples are arsenic, antimony, bismuth, phosphorus. Those are going to be called as donor impurities or pentavalent impurities. Coming to the donor impurities, we are going to call the pentavalent impurities as the donor impurities. Why? These pentavalent atoms contain 5 electrons, but the silicon and germanium contains only 4 electrons. If you consider the silicon, it contains 4 electrons in its outermost shell. In its outermost orbit contains only 4 electrons. That means it requires only 4 electrons to make a covalent bond with the adjacent atom. For example, if I take arsenic, Sb, this arsenic belongs to 15th group. That means it contains 5 electrons. It contains 5 electrons in its outermost orbit. So when you form a covalent bond with 4 atoms, so these 4 atoms are going to be sufficient to form a covalent bond. What about the 5th electron? It cannot form a covalent bond because the silicon requires only 4 electrons to make covalent bond with the adjacent atoms. But this arsenic contains 5 electrons in its outermost orbit. So 1 electron is free to donate. That's why we are going to call these pentavalent impurities as donor impurities. Okay. Next, acceptor impurities. So acceptor, trivalent impurities are going to be considered as acceptor impurities, because if you consider a boron, this boron contains only 3 electrons in its outermost orbit. But if you consider silicon, silicon contains 4 electrons in its outermost orbit. That means it requires 4 other electrons to form a covalent bond. But how many electrons are there in boron? Only 3 electrons are there. That means it requires 1 more electron to complete the covalent bond, to complete the crystalline structure. That's why it will accept 1 more electron. That's why we are going to call trivalent impurities as acceptor impurities. Donor impurities, example for donor impurities are, that means pentavalent. Donor is nothing but pentavalent impurities are phosphorus, antimony, arsenic, bismuth, and so on are there. An example of acceptor, these belongs to this donor impurities, this phosphorus, antimony, arsenic and bismuth belongs to 15th group. And acceptor impurities are nothing but gallium, indium, aluminium, boron and so on, etc. These belongs to the 13th group. And what about silicon and germanium? That these belongs to 14th group in the atomic table. Intrinsic semiconductor plus donor impurities. So when you add donor impurities to intrinsic semiconductor, we are going to get an extrinsic semiconductor, which we are going to call it as an N-type extrinsic semiconductor. Why we are going to call it as N-type? Because when you add a donor impurity, it contains extra electron. That means more electrons will be there. Electron is nothing but negative charge. That's why we are going to call it as N-type extrinsic semiconductor. For example, if you add acceptor impurities, that means trivalent impurity to an intrinsic semiconductor, then we are going to have absence of electron, because only 3 electrons are going to be presented in acceptor impurities. That means it will accept 1 more electron. That means 1 more electron is required here. Electrons are not sufficient here. The absence of that electron, we are going to call it as a positive charge. That's why we are going to call it as P-type semiconductors. Here the positive charges are going to be called as holes. We are going to call the absence of electron as hole. Because in case of acceptor impurities, it contains only 3 electrons, 1 electron is absent. That absence of electron we are going to call it as hole, and these holes are going to be treated as positive charges. That's why when you add an acceptor impurity to an intrinsic semiconductor, you are going to get an extrinsic semiconductor which is going to be called as p-type semiconductor. The extrinsic semiconductors can be classified into two types. One is n-type semiconductor, another one is p-type. These two are the extrinsic semiconductors. Let us discuss each one in detail. Coming to n-type semiconductor. How n-type semiconductor is going to be formed? When you add donor impurities to the intrinsic semiconductor. These donor impurities are also called as pentavalent impurities because they contain 5 electrons in its outermost orbit. What are the examples for pentavalent impurity? Phosphorus, antimony, arsenic and bismuth. These elements are donating the excess electron. Since it contains 5 electrons, 1 electron is excess. That means these will donate that excess electron, and such elements are called as donor or n-type impurities. Some of the silicon atoms are displaced by the donor atoms. Let us see. I have considered the silicon crystalline structure like this. Some few silicon atoms here. I am going to remove one silicon atom, and in place of that I am going to add an antimony atom. See here, I am going to add an antimony. Antimony belongs to the 15th group and its atomic number is 51. Okay, it is a pentavalent impurity. It is a pentavalent impurity. So, how many electrons are there in the outermost orbit? It contains 5 electrons in its outermost orbit. So, I am going to add as an impurity to the silicon crystalline structure like this. See here, if you observe, there are 5 electrons present in the outermost shell. How the covalent bonds is going to be formed? The silicon atoms form a covalent bond with the neighboring atoms, and all the 4 electrons are going to be form the covalent bonds here like this. Now, what about this electron? These are the covalent bonds. And what about the electron here? That electron is going to be called as a free electron. So, the 5th electron, which is not going to be form a covalent bond, is going to be called as a free electron. That's why we are going to call this arsenic as a pentavalent impurity. It contains excess electrons. And we are going to call this one as an impure semiconductor or extrinsic semiconductor, because here one impurity is going to be added. All are not silicon atoms. We have added an impurity. And what is the type of impurity here? Pentavalent impurity. That's why we are going to call it as an n-type semiconductor. This is an n-type semiconductor because it contains excess electrons or free electrons. Now, if you observe here, what are the majority charge carriers here? Electrons, because the more number of free, if you add more impurities, if you add one more arsenic, you are going to get one more electron. So, when you add impurities, more number of electrons are going to be present. That's why in case of n-type semiconductor, the majority charge carriers are nothing but electrons. So, if you observe here, see here, the positive signs are going to be bounded. That means they are not mobile, they are immobile. And what about the electrons? They are free. They can freely move from valence band to conduction band. So, in case of n-type semiconductor, we are having free electrons and immobile positive ions. That's why we are going to call it as an n-type semiconductor.
So, to make our semiconductors impure, we need to add impurities. And this process of adding impurities is what we call doping. So, doping is the process of adding impurities. So, we add impurities. And when we say impurity, what we mean is anything other than silicon. That's what we mean by impurity in general. And why do we add that? Well, it enhances its properties. It makes our semiconductor better. So the big question now would be what impurities to add. And by the way, when you add these impurities where you get an impure semiconductor, we're going to call that as extrinsic semiconductor. So impure semiconductors, the technical name is extrinsic. That's all. It's just a name. It's basically impure. But now the big question is, what impurities can we add? Can we add anything we want? Turns out not to be so. All right, so this is one of those rare moments in physics where a periodic table is going to get popped up. And if you look at the periodic table, you can see silicon is sitting right over there under group 14. And it turns out to really enhance its properties, to make a difference, we need to add either elements from group 13, that's one less, or from group 15, that's one more. Either these elements or these ones. And if you add these, you'll get one kind of impure semiconductor, extrinsic semiconductor. And if you add these, you get another kind of extrinsic semiconductor, impure semiconductor. Let's use phosphorus. If you look at phosphorus, notice that it has 15 electrons, one more than silicon. That means since silicon has 4 valence electrons, phosphorus will end up having 5 valence electrons. So here is our phosphorus atoms, 5 valence electrons. Let's just assume that the phosphorus is going to replace one of the silicon atom, and it's going to fit nicely over here. And when it does, notice that 4 of its electrons are going to nicely form covalent bonds with the neighboring silicon. And so these silicon are pretty happy because they really don't care whether it's silicon or phosphorus. All they care about is getting their 8 electrons, and they've got it. But the key thing to note over here is this 5th electron. That's going to be our focus. So what's going to happen to the 5th electron? Is it free to move through the crystal lattice because it's not bonded? Well, we have to be careful. We have to look at the energy level of that electron. So let's get back our band diagram. We've seen that at very low temperatures, our pure semiconductor, this is the band diagram for pure semiconductor, it would have completely filled valency band. So what is the energy level of this electron? Does it lie in the valency band? Does it lie in the conduction band? Where is it? That its energy level lies somewhere over here, right below, very close to the bottom of the conduction band. Right? So all these 5th electrons of all the phosphorus atoms would be at that level. So let me just show it that way. Now at first you might be like, wait, how is that possible? Isn't this the forbidden energy gap? Aren't electrons forbidden from being here? Yes, but those are the electrons of silicon. But phosphorus electrons will have its own energy levels, right? So it just turns out that the energy level of this will be over here. And so we need to now figure out what's going to happen. Well, at very low temperature, again, this is going to be acting like an insulator, because there is, again, notice that these electrons are not free. They are, because these are in the forbidden region, there are no energy levels available. But what happens when you come to room temperature? We've already seen that at room temperature in a pure semiconductor, some of the electrons from the valency band can absorb thermal energy and jump into the conduction band and become free. This is called as thermal generation. But now think of it this way. If these electrons can get if the thermal energy can excite these electrons, don't you think thermal energy can readily, more easily excite these electrons, this electron, these electrons, because the energy gap is so tiny? I mean, this energy gap, the forbidden gap, is about 1 electron volt for silicon. This is what? It turns out for phosphorus about, I don't know, about 0.05 electron volt. It is so minuscule that these electrons can be easily jumped into the conduction band. And as a result, it turns out that at room temperature, almost all the phosphorus atoms end up donating their 5th electron. So all of them will end up jumping into the conduction band. And notice, as a result, the addition of group 15 elements increases the number of electrons. Let's write that down. And this, by the way, is the summary of the whole thing. So long story short, adding group 15 elements is going to give you a lot more electrons than holes. Lot more electrons. That's it. That's the idea. Since we have ended up with a lot more electrons, the majority charge carriers are negative type electrons. This semiconductor is called N-type semiconductor. N stands for negative, so negative type. So whenever you hear this word N-type, what must come to your mind that N is telling that in this semiconductor, it's extrinsic, impure, it has a lot more electrons than holes. So Ne is way higher than NH. And since this phosphorus has donated an electron to the silicon for conduction, this impurity is also called as donor impurity. So all group 15 impurities are also called donors. Donor impurities. Okay, some names that we usually use. And this level at which the electron was before it got jumped into the conduction band, that we'll call that as the donor level. Donor level. And one last thing might be, why are we using group 15? I mean, if we bring back our periodic table, maybe we could have added group 16, sulfur. It has six valence electrons. That means I would get 2 free electrons, right? More electrons. Isn't that better? Well, answer is no. The key is to look at the donor level. The reason it works out with the group 15 elements so nicely is because it turns out for all these elements, the donor level is very close to the bottom of the conduction band. And as a result, the electrons, the extra electrons provided by the donors can be easily promoted to the conduction band. And that's therefore almost all of them will end up promoting. But if you look at any group 16 or group 17, if you do the math, it turns out that the donor level goes lower and lower and lower. Now imagine, what's the point of having a donor level so low? Promoting those electrons, even if you have twice the number or thrice the number, promoting those electrons will be very difficult, right? And so it would be totally besides the point. And so the whole reason for using group 15 is that its donor level is very close to the conduction band, the bottom of the conduction band.
Next, p-type. P-type is exactly opposite to n-type. We are going to add acceptor impurities. Example for acceptor impurities are gallium, indium, aluminium, boron, etc., which belongs to the 13th group in case of atomic table. And we are going to call acceptor atoms as trivalent impurity because the outermost shell contains only 3 electrons. These elements create holes because one electron is absent. That absence of electrons we are going to call it as holes, or the deficiency of electrons we are going to call it as holes. And we are going to call this type of semiconductor as p-type semiconductors because we will treat this hole as a positive charge. Okay, let's see how we are going to form here. I have considered the same crystalline structure and I am going to remove one of the silicon atom. In place of silicon, I am going to add boron impurity. So if you observe here, this boron contains 1, 2, 3. 3 electrons in its outermost orbit. So its atomic number is 5. So innermost orbit contains 2 and outermost orbit contains 3. So I am going to add a boron atom as an impurity. Now how the covalent bonds is going to be formed? So the covalent bond will form like this. Now here there is no electron to form a covalent bond here. This absence of electron we are going to call it as hole. The absence of electron present here. The absence of electrons present in case of boron atom is going to be treated as a hole. Okay. That means in case of p-type semiconductor we are going to have more number of holes. Since we are going to treat holes as a positive charge, the majority charge carriers in case of p-type semiconductors are nothing but holes. So here if you observe, the majority charge carriers are nothing but plus. The holes are indicated by plus sign. Those are free to move. And what about the electrons? There is no free electrons and all the electrons are bonded. That's why we have indicated that electrons inside a circle. So the electrons are immobile here and the holes are free to move. Okay, please remember that. So in case of n-type semiconductors, we are having free electrons and that's why we are going to treat the electrons as majority charge carriers. In case of p-type semiconductors, we are having free holes. That means there are holes to move. That's why we are going to treat the majority charge carriers as holes in case of p-type semiconductor. And in case of p-type semiconductors, electrons are the minority charge carriers. In case of n-type semiconductors, holes are the minority charge carriers.
Let's add boron to the party. Now, if you write the electronic configuration of boron, you will see that it has 3 valence electrons. We can quickly write and check that, confirm that. So since boron has 5 electrons, its electronic configuration would be 1s2, 2s2, 4 done, 1 more would be 2p1. So notice that its valence electrons are just 3. Oops. And so if you add boron to the semiconductor, a pure intrinsic semiconductor, and the way of adding that is again really complicated, we'll not get into that, then some of the electrons, some of the silicon atoms could be replaced by boron atoms, or at some places there won't be silicon atoms. We call them as crystal defect. No crystal is perfect. So at some places there will be vacant sites. So boron can just go and swoop in and fit over there. So we just assume that one of the boron is just going to replace one of our silicon. So let's remove one silicon atom and fit our boron into the mix over here. As the boron fits over here, notice because it has 3 valence electrons, it can nicely form covalent bonds with 3 neighboring silicon atoms. So these atoms are pretty happy. They don't care who it is because they have filled up their octet structure. But you can see that this silicon is not happy because it's not filled its octet structure. And the reason is there isn't one electron over here. It would have been great to have an electron. So you know what? This silicon desperately needs one electron over here. So there is a vacant site for an electron, which is not occupied by anyone, and it's desperate for an electron. The question is, what's going to happen? Can any electron from here swoop in over here? Can it do that? Well, again, we have to be careful. We need to look now at the energy level of this vacant site produced by boron. So let's get rid of this periodic table and let's bring back our band diagram. We've been using that a lot. This would be the band diagram at very low temperature of an intrinsic semiconductor. But now the moment we add boron, we were interested in what is the energy level of this site. Well, it turns out again, if you do the math, then that energy level is found to be very close to the top of the valency band. Can you see how this is beneficial for us? So what will happen at room temperature? If we were to get this all the way to room temperature, then one effect we've already seen in pure semiconductor that's going to happen here as well. There will be thermal generation. Some of the electrons will gain thermal energy and jump into the conduction band. But notice, since there's another energy available over here, some of the electrons can even jump from here to here. Does that make sense? Because this energy gap is incredibly small. It's much smaller than this energy gap. It's much easier for electrons to jump over here. In fact, what's going to happen is that almost all these vacant sites will now be completely filled by some or the other electrons. And as a result, all those will be filled up by some of the other electrons, and when they jump, they would leave behind a lot of holes. So over here, if we were to see it, we could imagine, say, this electron has jumped from here to here. Any electron can go like that. Anyone in the neighborhood can do that. And as a result, notice it has left behind a hole, and this hole now is in the valency band. It is free to move. So notice by adding our group 13 element like boron, we have now produced lots and lots of holes. Again, let's write that down. So this is the summary of the entire thing. Group 13 elements. If you add group 13 elements, then we end up with lot more holes than electron. And so, because now the majority charge carriers, the majority of conduction is done by holes which act like positive charges. Remember that they're not positive charge, they're not even particles really, but they act like positive charge in the sense that if you apply an electric field, holes appear to move in the same direction. So since you have a lot of positive type charge carriers, we call this as p-type semiconductor. P for positive. So we call this as p-type. And so whenever someone says p-type, what comes to my mind? That p is telling me there are a lot more positive type. Positive type means holes. So a lot more holes, NH, number of holes is way, way larger than number of electrons. Number of electrons. And that's pretty much it. We just have a couple of names, technical names that we use when it comes to adding impurities. The process of adding impurity is called doping. And since this boron, it accepted an electron, and that's how we got holes, we call this impurity as an acceptor impurity. Right? We also call this as group 13 are called as acceptors. Acceptor impurities are just acceptors. And the level, the energy level that they had, at which the electrons were able to jump into, that energy level that boron introduced is called the acceptor level. So it's called acceptor level. And now we could ask a big question. Why are we only adding group 13 elements? I mean, if we bring back our periodic table, I mean, group 13 elements is fine, but why not add group 12 elements? Say like, I don't know, zinc maybe, because if you work out its electronic configuration, you will see it has just 2 valence electrons. You can just check that. And so if we added zinc maybe, then it has only 2 valence electrons and it will have 2 vacant sites. Yay, more electrons can occupy, right? No, it doesn't work that way. What's important is to look at that acceptor level. It turns out that if you add group 12 elements or any other group elements, the acceptor level will just go higher and higher and higher. What's the point of having multiple vacant sites, a lot of vacant sites, if your acceptor level is so high? because then it'll be extremely difficult for these electrons to jump from here to here. It'll take a lot more energy, and so most of those will not be occupied by the electrons at room temperature, and so the whole thing will be pointless. And that's the real reason why we only add group 13 elements, because in group 13 elements, it turns out that the accepted levels of all these elements, almost all these elements, the accepted levels are very close to the top of the valency band, and that's really the key to understanding why. That's the key to why we add group 13 elements.
So that's all about semiconductors as well as intrinsic and extrinsic semiconductors. Thank you.